to talk about Hochschild homology for green functors.
Thank you very much. So I am the third talk before lunch, so I tried to make this talk friendly, but let me know if it ceases to be friendly, and I will try harder. So I'm going to talk about Hochschild homology for green functors, and the work that I'm going to talk about is joint with Andrew Blumberg, Mike Hill, and Tyler Lawson. So I want to start by just telling you what the goal of the talk is going to be, and then I'm going to back up and motivate why you would want to do the thing that I'm going to tell you that I'm going to do. So let me just start with the overarching goal. So here's my goal. I'm going to talk about a construction today, and this is for, so I'm going to let H and G be finite subgroups of S1, and I'm going to consider R a green functor for H. And what I want to talk about today is a definition, so I'm aiming to define a G-twisted version of Hochschild homology for R. So I'm going to write that as the G-twisted Hochschild homology of my H green functor R. Okay, so I'm going to get to that, but I'm going to step way back and first motivate why you would want to consider such a thing. And the motivation for this construction is going to come out of an interest in algebraic K-theory and topological Hochschild homology. So let's look back and recall a little bit about how algebraic K-theory and THH are related. So let's say we're interested in studying a ring A. So I'm going to let A be a ring, and I want to think about, say we have a goal of computing algebraic K-theory groups for A. So we're interested in the algebraic K-theory groups of A. So algebraic K-theory is known to be very difficult to compute, but one approach to computing algebraic K-theory is via what's called the trace methods, where we try to approximate this thing by friendlier invariants of that ring. So a first approximation that you might make is you might say, well, how does algebraic K-theory relate to a familiar ring invariant, which is Hochschild homology? So it turns out there is a relationship. There's a map like this. This is called the Dennis trace map. And we could view Hochschild homology as some kind of approximation to algebraic K-theory. Now, bear with me as I'm actually going to recall the definition of Hochschild homology because it's going to be important for us going forward. So let's just remember how Hochschild homology of a ring is defined. So I'm going to start by defining the cyclic bar construction on a ring. So the notation I'll use is B sic A for the simplicial abelian group defined as follows. So in simplicial level Q, this thing will be Q plus 1 tensor powers of A. And then it has some face and degeneracy maps. So let's recall how those face and degeneracy maps go. So let's start with face maps. So we have face maps DI. And so this takes something of the form A naught tensor through AQ. And what the ith face map does is it's going to multiply the ith and the I plus first element together. So this is going to go to A naught tensor AI times AI plus 1 tensor AQ. And that makes sense as long as I is greater than or equal to 0 and less than Q. The last face map's a bit different, so recall that the last face map brings that last element around front and then multiplies. So we have AQ A0 tensor A1 through AQ minus 1 if I is equal to Q. We also have degeneracy maps, SI. And degeneracy maps just insert a unit. Oh, I don't even need that. So they're going to insert a unit after the ith coordinate, like so, and that makes sense for I greater than or equal to 0 and less than or equal to Q. Okay, so we have these face and degeneracy maps that make this into a simplicial abelian group. We actually have an additional operator that I want to mention as well, which is that we have a map which I'll call TQ on the qth simplicial level, which is a cyclic operator. So what this thing does is it's just going to permute my coordinates by bringing the last coordinate around to the front. So T applied to this gives me AQ tensor A0 through AQ minus 1. Okay, so we have this simplicial abelian group, which is the cyclic bar construction, and I'm trying to define for you Hochschild homology. So how does that go? Well, one thing I could do is I could get a chain complex from this simplicial abelian group, and I'll denote that as C. So that's the chain complex where I look at this cyclic bar construction on A, and I take boundary map to be the alternating sum of the face maps. And so what is Hochschild homology? Well, the ith Hochschild homology of a ring A is the ith homology of this chain complex. Or we know by the Dold-Kahn theorem that equivalently we could say this is the ith homotopy group of the geometric realization of the simplicial bar construction. Okay, so two different ways to view the same thing. Now, I mentioned this cyclic operator because I want to make a note now, which is that this is not just a simplicial abelian group. This is actually, the cyclic bar construction is a cyclic object, hence the name. And why that's important for us is by Kahn's theory of cyclic sets, when we geometrically realize a cyclic object, we get an S1 action. So that tells us that the geometric realization of the cyclic bar construction has an S1 action. Okay, so this is ordinary Hochschild homology. And we have this trace map relating algebraic K-theory, and so I said maybe our original goal was to understand something about algebraic K-theory. And Hochschild homology, you know, in some sense is an approximation to algebraic K-theory, but you wouldn't expect this to be a very good approximation. This is a purely algebraic construction. We know that algebraic K-theory is sort of topological in nature. So to get a better approximation for this, we might ask, well, can we come up with a topological version of this construction? And of course, now we know that you can, and that's called topological Hochschild homology. So topological Hochschild homology was originally constructed by Bäckstedt. And I'll say in a minute a bit about the definition, but what do we get out of topological Hochschild homology? Well, we get a trace map. So we have a trace map from the algebraic K-theory of A to the topological Hochschild homology of A, which is a factorization of this Dennis trace map to Hochschild homology. So this first map, the trace map to topological Hochschild homology, is often called the topological Dennis trace. And this map relating THH and HH is called linearization. Okay, and topological Hochschild homology is indeed a better approximation to algebraic K-theory than Hochschild homology was. So what is THH? Well, what's the idea? So what I gave you over here is an algebraic construction, and what we know how to do as algebraic topologists is take algebraic constructions and translate them into topology. So we have a machine that does that, right? What do we want to do? Well, I had a bunch of rings over here. So where I had rings, I should replace them with ring spectra. And where I had tensor products over there, I should replace those with smash products. Okay, and that should be some mechanism for translating my Hochschild homology construction into a topological version. So if you did that, what would be the definition that you'd come up with? Well, you'd say something like, if R is a ring spectrum, then the topological Hochschild homology of R should be the geometric realization of the cyclic bar construction on R, which makes sense as a thing to say. Up here I have topological Hochschild homology of a ring. So just by convention, when we talk about topological Hochschild homology of a ring, what we mean is topological Hochschild homology of the Eilenberg-MacLean spectrum of that ring. Okay, so that makes sense as a definition, but a thing that gets confusing in the history of this field is that this is not Bäckstedt's original definition. So why not? Well, Bäckstedt defined THH in the early 90s, and at the time, he didn't have the luxury of a nice category of spectra with an associative smash product, and so he couldn't do this. So Bäckstedt's original definition, he developed a lot of coherence machinery to sort of mimic this without defining it in this sort of more straightforward way. But the interesting thing is that for years, we have continued to use Bäckstedt's construction of THH in the field of algebraic K-theory because it has a really important property. So what do we want out of THH? It turns out that what we need out of topological Hochschild homology, if you have an eye towards algebraic K-theory, is you want THH of A to be what's called cyclotomic. Okay, so what does that mean? So in other words, so one characterization of what it means to be cyclotomic is as follows. So THH is cyclotomic if THH of A is a genuine S1 spectrum with compatible equivalences that look like the following. So we have equivalences from the CN geometric fixed points of topological Hochschild homology back to topological Hochschild homology. Let me put a rho n star there for accuracy. So we want maps like this for all n, and they need to be compatible in some way. Okay, so I should mention, of course, that, so this is sort of a classical notion of what it means to be cyclotomic. Recent work of Nicklaus and Schulze give us a new characterization of what it means to be cyclotomic as well. So I'm not going to say so much about that today. Okay, but we want THH to be cyclotomic, and Bäckstedt's construction of THH is. So Bäckstedt's THH has been known for a long time to be cyclotomic. So why does that matter? So what is the importance of being cyclotomic to this story? Well, it goes back to this idea of approximating algebraic K-theory. So THH being cyclotomic allows us to define an even better approximation. So the point is that being cyclotomic allows for a definition of the next approximation, which is topological cyclic homology. And topological cyclic homology was originally defined by Bäckstedt, Chang, and Madsen. So let's just briefly recall how that goes, because that's going to be important for us as well. Okay, so topological cyclic homology. Well, where were we? We had algebraic K-theory, and we had this map to topological Hochschild homology. That was the topological Dennis trace map. Now, THH is going to be an S1 equivariant object because it's the geometric realization of something cyclic, and so we could look at fixed points under that S1 action, or actually under subgroups of that action. So for instance, I could consider the CP fixed points of topological Hochschild homology, and I could ask the question, well, how is that related to THH? Well, one answer to that question is I have a map induced by inclusion of fixed points, right? So that's a straightforward map. We write that as F, and we call that the Frobenius. So in my picture here, that means I have fixed points and a Frobenius map. I could keep going. I have CP squared fixed points, etc. I have Frobenius maps like this. And it turns out that this topological Dennis trace lifts through these fixed points. So far, I'm good if THH is just some kind of S1 equivariant spectrum. But at the next step, I have another map, which is called R, which is a map, again, from the CP fixed points to THH. This one is called the restriction. And to define the restriction map, we need to know that THH is cyclotomic. So I'm not going to go in, we're not going to dive into how to define the restriction map, but it's where we use the topological Hochschild homology as a cyclotomic spectrum. So the restriction map fits in my picture as well. And Bäckstedt, Chang, and Madsen define topological cyclic homology as follows. So topological cyclic homology then, let's say, of A at a prime P is the limit over these restriction and Frobenius maps of fixed points of THH. So, sorry, in my picture, topological cyclic homology should go all the way up here. And this topological Dennis trace lifts all the way to topological cyclic homology, and this is the map that's called the cyclotomic trace. Okay, so a lot of algebraic K-theory computations that have been done in the past few decades have been done via these trace methods, and the idea is that TC should be computationally more approachable. And we have comparison results telling us about the cyclotomic trace map. For instance, due to McCarthy, Dundas, Hesselholt and Geisser, various people have different maps about how close that cyclotomic trace is to being an equivalence. Okay, so before I go on, I want to just make one more comment, which is that when you're actually doing these algebraic K-theory calculations, these fixed points at THH end up playing an important role, as you can sort of guess from that diagram. So much so that when I look at these homotopy groups, there's another name for this as well. So these are called often TRN plus 1 QA at the prime P. Okay, so that's just notation. But I want to just point out, and it will come back, that we have some operators on this thing. So in my diagram up there, you can see this had a map F and a map R to TRNQ of A at P. And there's another map as well, which is called the Verschiebung, which is the equivariant transfer. Okay, so keep that in mind. Okay, so what is the point? The point is that having this cyclotomic structure is important in order to be able to use topological Hochschild homology with these algebraic K-theory calculations. Okay, and for a long time, no one knew how to put a cyclotomic structure on the sort of cyclic bar construction definition of THH that you would make most naturally. So we continue to use Bachstad's definition. So a theorem of Witt, Andrew Blumberg, myself, Mike Hill, Tyler Lawson, and Mike Mandel, says in essence that using the Hill-Hopkins-Ravenel norm, now you can construct a cyclotomic structure on this cyclic bar construction version of topological Hochschild homology. So more specifically, let's say R is a cofibrant orthogonal ring spectrum. Then what we show is that the cyclic bar construction of R, the geometric realization of this cyclic bar construction on R, let's just say, is cyclotomic. So let me make that slightly more accurate by throwing in a change of universe functor here. But maybe we won't worry so much about that right now. And the spirit of this is that you should think of this as being the norm from the trivial group to S1 of R. Okay, so this says that this cyclic bar construction definition is indeed cyclotomic. Similar work was done around the same time by Martin Stolz. Yes?
If for me an S1 spectrum happens to be an orthogonal spectrum with S1 action, is this then the thing I can ignore? Can I then ignore this change of universe? What is this doing?
No, I mean, so the cyclic bar construction is naturally going to give me something that is indexed on R infinity, right? Because it's going to give me something that's like...
If you know, you could take an S1 spectrum to be an orthogonal spectrum with S1 action and then the appropriate definition of equivalence. Is it then simply the bar construction?
So let me come back to that, because we're going to talk in a minute about what happens if you feed this kind of construction in equivariant spectrum. So I think I'm going to get back to your exact question in a moment. Okay, so Martin Stolz did some similar work around the same time. And then in very recent work of Dotto, Malkovich, Kachkoria, Sagave, and Wu, they show that this cyclotomic structure, I'm going to say this in a sketchy way, so they show that the cyclotomic structure on the cyclic bar construction, so on this cyclic bar construction definition, agrees with Bachstad's cyclotomic structure. Which means in particular, so like Nikolaus Schulte check that their cyclotomic structure in topological Hochschild homology agrees with Bachstad, so this implies that all three agree. Okay, so what does that mean? It means we don't really lose anything by thinking about topological Hochschild homology from this cyclic bar construction perspective. So we still have the cyclotomic structure that we wanted. And the nice thing about this cyclic bar, or one nice thing about this cyclic bar construction perspective, is that it lends itself to generalizations. So in that same work of Engelveit, Blumberg, Gerhardt, Hill, Lawson, Mandel, we define a couple different sort of relative versions of topological Hochschild homology, and I want to tell you about one of them now. So I'm going to generalize topological Hochschild homology in the following way. So THH was something that we could feed any ring spectrum. Now I'm going to look at a version where R is a CN ring spectrum, so CN equivariant ring spectrum. And I want to define a Cn relative version of topological Hochschild homology. So what should this thing be? This should be something where we feed it a Cn equivariant object, and it should spit out something, again, S1 equivariant. So topological Hochschild homology should be S1 equivariant. So I should think about this. The idea here is we're trying to think about the norm from Cn to S1 of R. So that's sort of the idea. Okay, but we want to construct this more explicitly. So how do we explicitly construct? Okay, so I'm going to let R be a Cn ring spectrum, as I set up there. But now here I'm going to look at a Cn ring spectrum indexed on the trivial universe. And what I want to define is a Cn twisted version of the cyclic bar construction of R. Okay, so what is this thing going to be? So on the qth level, as we would expect, this is q plus 1 smash powers of R. And the degeneracy maps are just the same, so the degeneracies are the usual thing, analogous to what we did in the algebraic construction of Hochschild homology. The face maps, however, are a bit different. So to describe the face maps, I need a little bit of notation. I'm going to let little g be the generator e to the 2 pi I over n of Cn. And I'm going to define a map alpha q Okay, I'm going to define a map alpha sub q on the qth simplicial level, so from q plus 1 smash powers of R to q plus 1 smash powers of R. And alpha q does two things. So the first thing it does is it's going to bring the last factor to the front. And the second thing that it's going to do is it's going to act on that new first factor by little g. So act on the first factor by little g. Okay, so a picture of that schematically. I have a bunch of smash powers of R. I'm going to bring the last one to the front, and I'm going to act by my generator little g. Okay, so I need to tell you now what the face maps are, and most of them are just the usual thing. Okay, so the di's are the usual thing. They multiply the ith and I plus first factor as long as I is less than q. And then that last one is strange again. So what does the last one do here? So my last one, so remember in the ordinary cyclic bar construction, the last one brought the last factor to the front and multiplied. So now the last one is going to bring the last factor to the front, act by little g, and then multiply. So it's going to be alpha q composed with d naught. Okay, and so this gives us a simplicial object. But the cyclic bar construction, you know, was cyclic, and this thing is no longer cyclic. So the Cn twisted cyclic bar construction is not cyclic, but we could ask, what kind of structure does this thing have? Well, let's notice a couple things. So alpha q generates a, let's get this right, Cn times q plus 1 action on simplicial level q. And you can also check that alpha q behaves nicely with respect to face and degeneracy maps. So plus there are some relations. I'm not going to write them all, but let me write one so you can see sort of what they're like. So if you do alpha q followed by di, that's going to be di minus 1 followed by alpha q minus 1. If I is, I think that. No, yes, maybe, don't quote me on that. So we have relations of that form and how these things commute with the face and the degeneracy maps. Okay, so the alpha q generates this action and we have a bunch of relations like this, and it turns out that this is some known structure. So what kind of structure is that? Well, this is what's called This is a lambda n op object in the sense of Bäckstedt, Chang, and Madsen. Okay, so where does this kind of object come up for them? Well, this kind of object comes up when you do edgewise subdivisions. So that's how they see it in their work. We have a structure like this here as well. If you let n equal 1, this is a cyclic object. Okay, so this is some kind of generalization of what it means to be cyclic. And nicely, Bäckstedt, Chang, Madsen tell us what happens when you geometrically realize something like this. So they prove in that original paper about TC that the geometric realization of an object like this has an S1 action extending a simplicial C action. Okay, so you can probably see where I'm going with this. I'm trying to define my topological Hochschild homology, and again, we're going to define it as a geometric realization of a cyclic bar construction, but now we have this twisted cyclic bar. Okay, so what is the definition then? So I have R, a Cn equivariant ring spectrum, and what I want to say is that the topological, the Cn relative topological Hochschild homology of R should be the geometric realization of, the Cn twisted cyclic bar construction on R. Okay, and maybe to make that actually make sense, I need to add a few things. So this Cn twisted cyclic bar construction was something that we did to Cn spectra indexed on a trivial universe. So here I'm going to change universes to some trivial universe, and then I'm going to change universes to some complete universe out here. Okay, but what we get from this is a Cn relative version of topological Hochschild homology. And the natural one question you might ask is, well, does this give you something cyclotomic? So what we check is that if n and p are relatively prime, then we get something which is called p cyclotomic, which means like cyclotomic at the prime p. And that allows for a definition of Cn relative topological cyclic homology and Cn relative TR, for instance. But then it brings you to wonder. So in the original story, we had Hochschild homology, right, which was this algebraic analog, and then we took its topological analog. And then I did some kind of generalization of the topological analog, but I've stepped away from that algebraic Hochschild homology. And so a natural question then is, well, does this Cn relative topological Hochschild homology, does it have an algebraic analog? So that's the question that's going to lead us to our goal over there. So the question is, what is the algebraic analog of the Cn relative THH? Okay, and before we can answer that, I guess we need to ask ourselves, what do we want out of an algebraic analog? Like what would make us happy to have in order to call it an algebraic analog? Well, for that, let's return for a moment to the classical case. So when A was a ring, what did I say happened? Well, I said we have a map from THH of A to the Hochschild homology of A. So this was called linearization. And remember that THH of A is really THH of the Eilenberg-MacLean spectrum of A. It's just notation. So we had this map. It was called linearization. And the thing that I didn't mention earlier is that this map is an isomorphism when k is 0. So on pi naught, so we get an isomorphism from pi naught of THH to the 0th Hochschild homology of A. Okay, so those are some classical things. So if I want an algebraic analog of my Cn relative THH, I would like to have a statement like this. I'd like to say there's a linearization type map to something in algebra that induces an isomorphism on pi 0. So that's what I'm after. Okay, but how do I get an Eilenberg-MacLean spectrum of something that's going to give me a Cn equivariant ring spectrum? Well, for that, maybe the thing that I want to apply Eilenberg-MacLean spectrum to is a green functor. So I'll recall a bit of basics about Mackey functors in a minute, but for now, let's just say let R be a Cn green functor Then when I take its Eilenberg-MacLane spectrum, HR, I'm going to get a CN ring spectrum. And so something that would convince me that I have the right algebraic analog would be if I have a linearization map from the CN relative THH of the Eilenberg-MacLane spectrum of R, so that makes sense, to some kind of Hochschild homology, CN Hochschild homology of the green functor R. And this is where now the question is, like, what is this? So what does it mean to take Hochschild homology, CN twisted Hochschild homology of a green functor? Okay, so maybe now it's clear why we want to achieve this goal, which is that I want to be able to, for a green functor, to define some twisted version of Hochschild homology for that green functor. Yeah?
Can I ask a question? So when you have a green functor which is not a Tambara functor, then HR in your model you're working with orthogonal spectra, you cannot make it strictly commutative.
I don't need it to be commutative. So I didn't assume that R was commutative for, like,
so
it's like THH. You don't need a commutative input. Yeah, you're right. So R is not, I mean, HR is not necessarily going to be commutative, but doesn't matter for us.
Do you also get a Blockstadt spectral sequence?
So I'm going to come to that. Actually, the answer to that is that I don't know. So you get some spectral sequences out of this from, like, the Lewis-Mandel style homological algebra for Mackey functors. I haven't thought about whether you get an actual analog of the Blockstadt spectral sequence, but you get, for instance, like the standard, like, Kunith type spectral sequence that you get for THH, which has E2 term Hochschild homology if you assume flatness conditions and stuff like that. Okay, where was I? Right. So what is this thing? Okay, let's recall a few things about Mackey functors. So people have been talking about Mackey functors all week, but we haven't written down some sort of basic facts, and I'm going to need them, so maybe I'll write down some basic things. Okay, so let's let M be a Mackey functor. M, a Mackey functor. So what does that mean? Well, roughly, how can we think about this? So one way to think about Mackey functors is to say that we have two functors, M lower star and M upper star, from finite G sets to abelian groups, where one of these functors is covariant, one of them is contravariant, and the values have to agree on objects. So if I look at this on objects, they have to agree, and we call that M lower bar of X. Okay, and so for instance, if I have K sitting inside H sitting inside G subgroups, I have maps like, I have map of the orbit G mod K to G mod H. And what does that give me on the Mackey functor M? So that associated to the orbit G mod H, I can evaluate there, I can evaluate at G mod K. And let's do this right. So the covariant and the contravariant functor are each going to induce a map from this map. So the one induced in this direction is called the restriction. And the induced map in this direction is called the transfer. Okay, so I have a structure like this, and then I'll just say plus axioms, which I'm not going to go into, that make up what it means to be a Mackey functor. So what's an example of a Mackey functor? Well, the classical first example is representation rings, but maybe for us, the first example, or an example, is to think about equivariant homotopy groups. So for example, if you have X, a G spectrum, then I could define a homotopy Mackey functor, so this would be a G Mackey functor on X. And what is this when I evaluate it on orbits? Well, at the orbit G mod H, this is pi k of the H fixed points of X. Okay, and those, turns out, fit together to give you a Mackey functor. So I claim that we've actually already seen a Mackey functor earlier, although I didn't frame it in that way. But what does this mean? Well, I can do this for any G spectrum. So in particular, I could plug THH into this machine, and it would tell me about fixed points of THH, Well, we already did that. We already looked at fixed points of THH, and we called those TR groups. So an example of this example is that TR is a Mackey functor. Mackey functor. And we had these maps. If you think back, I had this picture that, let's say TRQ. We had A at P. Sorry, trying to be a little less sloppy. We had these maps on TR earlier, right? We had Frobenius, restriction, Verschiebung. And so you might ask, well, how are those related to the Mackey functor structure? And there's a very unfortunate notation clash that arises here in that the Frobenius map is the restriction in the Mackey functor. There are reasons that this one's called, whatever, it's just, it turned out this way, but I can justify it, but also I can argue that it's bad, so it can go either way. But the Frobenius is called the restriction. The Verschiebung is the transfer, and this restriction map in TR is not part of the Mackey functor structure. So that's going to come up for us later. So just remember that this thing coming from the cyclotomic structure does not come as part of the Mackey functor. Okay, so we already saw one example of a Mackey functor. Okay, what else do I need to know about Mackey functors? So one thing about Mackey functors that's going to be important for what we're doing is the following. So if you look at a Mackey functor M at the orbit G mod H, so this thing has an action of the Weyl group. So this gets an action of the Weyl group induced by automorphisms of the orbit G mod H. Now, in our situation, we're going to be interested, as you see, in subgroups of S1. So we're interested in cyclic groups. And if G is cyclic, what is the Weyl group? Well, if G is cyclic, this is just the quotient G mod H. So in particular, if you're working with a cyclic G, these, at every G mod H, this has a G action. And the restriction in the transfer maps are maps of G modules. Okay, so what it means is that the Mackey functor itself, we can view M itself as having an action of G. Okay? And one other thing that I need is, so I've said some stuff about Mackey functors, but what our goal was related to green functors, so let's just recall what a green functor is. So Mackey functors have a symmetric monoidal product. That symmetric monoidal product is the box product. And so what is a green functor? A green functor is a commutative monoid in this category. Okay. So it's a Mackey functor with a way to multiply. So what does that allow me to do? Well, in particular, that allows me to make sense of a cyclic bar construction type construction. Okay, so what do I want next? I want to define a cyclic bar construction, a twisted cyclic bar construction for these green functors. So I'm going to try to mimic now in algebra what we did in topology. So I'm sort of going in the opposite direction of what we did earlier. And so let's let G be a subgroup of S1 and R G green functor. Okay, and what I want to define then is I'm going to define the G twisted cyclic bar construction on the green functor R. And you may, if you've been paying attention, you may be able to guess how this goes. So what should it be? Well, on the qth simplicial level, this should be q plus 1 now box powers of R. And then what are the face maps going to be? Well, what are the DIs? So the DIs, they multiply the I and the I plus first factor, which still makes sense here. So they multiply, let's just say the usual thing. The usual thing as long as I is less than Q. And just as before, the last one is different. So what does the last one do? Well, I should set notation. So I'm going to let little g be e to the 2 pi I over the order of g, a generator. And so what does the last one do? Let me just draw a picture. So I have something that looks like this. The last one brings the last factor to the front, acts by little g, and then multiplies. Okay, so that's our DQ face map. Okay, so this gives me a twisted cyclic bar construction. And in order to define my G-twisted Hochschild homology, I need just one more piece then.
What's acting by G on the G green function?
Right, yeah, so that was the point of this. So this, right, in general, oh, these are, sorry, in general that doesn't make any sense, right, to act on G, to act by G on some green functor. So this is something special about the fact that we're working with a cyclic group, and so the Weil groups are all quotients, and so we get a G action on the Mackey functor and hence on the green functor. So, so yeah, there is something specific here about the fact that we're working, this construction will not work if you work in a setup where the Weil group is not the quotient. Oh, and maybe I'll mention that, so we do a more sort of homological algebra, a more general homological algebra setup here where we define a twisted cyclic nerve where you can add a bimodule coordinate or you can use any G, not necessarily a generator, but this is what I need for today, so stick with that. Okay, so this was, if you had a G green functor, you get a cyclic bar construction. But if you look at my goal was I wanted to be able to take an H green functor and get a G twisted theory out of it. So this isn't quite going to do it. I still need one more missing piece, and that is that I need a notion of norms on Mackey functors. Okay, so one notion of norms on Mackey functors, so let me just say one definition, is due to Hill-Hopkins. And this looks like the following. So let's let H be a subgroup of G and M a Mackey functor for H. And what I want is I want a norm from H to G of the Mackey functor M. So I want to feed this thing an H Mackey functor, and I want it to give back to me a G Mackey functor. And how can we do this? Well, the Hill-Hopkins definition really capitalizes on the fact that we have a sensible norm in spectra. So how can we use the norm in spectra to do this? Well, I have a Mackey functor. I have an Eilenberg-MacLane spectrum associated to that Mackey functor M. So that gives me, for an H Mackey functor, gives me an H equivariant spectrum. And then I know how to do norms in spectra, so this is now a norm in spectra. But I want this thing to spit out a Mackey functor, and the Mackey functor I want is the Mackey functor pi 0 on that. Okay, so that's a definition of what it means to take a norm in Mackey functors. That's sort of abstract though, so we may ask, are there more algebraic constructions? And there are. I'll reference them, something more algebraic in a couple minutes, but let me note here while I'm giving references that there are more algebraic constructions of the norm, for instance, due to work by Kristen Mazer and Rolf Hoyer. They give sort of more explicit constructions of what it means to take a norm. Okay, now we are ready to define our G-twisted Hochschild homology. Okay, so what is the definition of this thing then? So again, my setup, which I have over here, is that I'm looking at finite subgroups of S1. R is an H green functor. And then to define the G-twisted Hochschild homology of R, this is going to be the homology of my twisted cyclic bar construction, so the G-twisted cyclic bar construction. So this thing takes a G Mackey functor, so of the norm from H to G of R. Okay, so this gives me some G-twisted version of Hochschild homology. And then the question is, well, how do we know if that's the right thing? So is this the algebraic analog that I was looking for? And I say yes. So what do we show? Who is it? Blumberg. I'm bad at alphabetizing. So what do we show to argue that this is the right thing? Well, what did we want? So we wanted to know that if you took, let's say, H relative THH of an Eilenberg-MacLane spectrum of a green functor, then we should have a linearization map to Hochschild homology, the G Hochschild homology of R. So here R is an H green functor. And so on the left, to make this make sense, I look at the G Mackey functor of homotopy groups on that. And I put a K over here. Okay, so we show that yes, we do have a linearization type map relating the topological theory to this algebraic theory. And remember, we wanted it to be an isomorphism on pi 0, so we have that as well. So pi 0 of H relative THH of HR is twisted HH0 of R. But that's not, I mean, so this just maybe, this is an argument that we have the right thing, but remember H relative THH was something we could do for any H equivariant spectrum. So I'd like to ask, well, what if I plug in something that's not an Eilenberg-MacLane spectrum? What happens then? So let's let R be a -1 connected commutative ring spectrum. Then we get linearization maps in that situation as well. So in that case, it looks like a map from the H relative THH of R to the G twisted Hochschild homology of the Mackey functor pi naught of R. Okay, and that also induces an isomorphism on pi naught. Okay, so that's an argument that this is the correct algebraic analog. So it receives linearization maps from relative topological Hochschild homology in exactly the way that you would want it to. Let me just do a really short example of applying this to an actual Mackey functor. So let's, for instance, let's look at FP. So FP is a ring. So I'm going to consider that as a green functor for the trivial group. So this is a trivial green functor. And I'm going to ask, well, what's the Cp to the n twisted Hochschild homology of Fp? So what does that mean? Let's unpack that for a minute. So that means I'm supposed to take the homology of the Cp to the n twisted cyclic bar construction on the norm from the trivial group to Cp to the n of the trivial Mackey functor Fp. Okay, so that's what I'm asking, whether or not we can compute that. Okay, and this thing we actually can compute. So the first thing is to understand, well, what is this Mackey functor norm? So what is the norm of Fp? So I mentioned, and maybe it's still there, yeah, that there were some more algebraic constructions of the norm, in particular one due to Kristen Mazur. So in Kristen Mazur's algebraic construction of the norm, she has this framework, particularly for norms involving cyclic groups, cyclic p groups. And so, and even in her paper about this, she computes the norm from E to Cp of Fp, so a very related computation. But you can use her framework to extend that relatively easily. So using Kristen Mazur's framework here, you can find out that on an orbit, try again, Cp to the n mod Cp to the k. This thing is z mod p to the k plus 1. Okay, and then we need to know also like restriction.
Groups or Eilenberg-MacLane spectra on the left-hand side, or is this a calculation in algebra or the spectra?
This is a norm in Mackey functors.
Okay.
I'm considering this as a trivial Mackey functor for the trivial group, and I'm taking the norm in Mackey functors. Okay, so the restriction maps are the quotients, canonical quotients. The transfers are multiplication by the index. And for us, understanding the Weil group actions is important as well, and in this case, the Weil group actions are trivial. Okay, so we can explicitly understand what is this norm of Cp, and then if you put it into the cyclic bar construction, the twisted cyclic bar construction, in this case, you can just compute what it is. So
this computation doesn't depend on n?
No. So if we put it into our cyclic bar construction, here's what we find. So we find that the twisted Cp to the n Hochschild homology of Fp is, so this is going to spit out some Mackey functor, and the Mackey functor that it spits out is this norm of Fp when k is 0 and 0 otherwise. Okay, and we completely understand that Mackey functor, so that's a very explicit calculation of this twisted Hochschild homology. So one thing to notice over here. So if you look at HH0 of my twisted CP to the n of FP, okay, so it's supposed to be the norm here, and I have an explicit calculation of that norm. So if I evaluate this at the orbit CP to the n mod CP to the n, what do I get? I get z mod p to the n plus 1. And if you're a Witt vector kind of person, this might start to feel really familiar to you. So what we're seeing here is actually that this thing is the p-typical Witt vectors of length, I always get this wrong, n plus 1, let's say. I think that's right. So this is length n plus 1 p-typical Witt vectors. And I'm going to write that in another way, which will seem strange for the next minute, which is that you can also write that as the big Witt vectors on the truncation set of natural numbers that divide p to the n. So that's a different way of writing the same Witt vector construction. Okay, and the reason that I wrote it that way is because this is not just a fluke. This is an example of a more general phenomenon that we see from our twisted Hochschild homology, which is that HH0 of Cn for any a commutative ring, when you look at that at the orbit Cn mod Cn, what you get out is the big Witt vectors on the truncation set of natural numbers that divide n. So if you're not in this area, that might seem like a weird connection. If you are in this area, you'll think, oh, well, it's not so surprising that we see Witt vectors here. And why is it not so surprising? Well, it's not so surprising because we see Witt vectors in the classical story. So Hesse-Holt and Madsen have a theorem that says that if you have a commutative ring, when you look at pi 0 of the Cp to the n, let's do Cn, fixed points of topological Hochschild homology, that gives you the big Witt vectors of length n, or let me say something meaningful, the big Witt vectors on the truncation set of natural numbers that divide n for your ring A. So this is an important theorem in trace methods, and this is, in some ways, this theorem is the reason why we have the Frobenius restriction naming the way that we do, is because it agrees with the Frobenius restriction naming on Witt vectors. But so we might want, or we would want, from our theory, a similar result. We would want that pi 0 of our relative topological Hochschild homology somehow is Witt vectors. And that motivates a definition. So that says that maybe the correct definition of Witt vectors in this setting should go as follows. So if I have R and H green functor and H a subgroup of G, these facts suggest that we can define a notion of G Witt vectors for this green functor. And what should the G Witt vectors be? Well, the G Witt vectors should be the G twisted Hochschild homology of R, HH0. And if you make this definition, if you define G Witt vectors in this way, then you get exactly the result that you want, which is that if R is a -1 connected commutative H spectrum, H ring spectrum, then when you take pi naught of the H relative THH of R, what you get is the G Witt vectors of Mackey functor pi naught on your ring spectrum R. Okay, so this is a lot of notation, I know, but this is an analog of the Hesse-Holt-Madsen result. So you can think of the Hesse-Holt-Madsen result as being like the H is the trivial group version of this, and this is building off of this. Okay, I think I have 5 minutes, and in the last 5 minutes, what I want to say is the following. So what I've done so far is we've defined this new algebraic construction that is an algebraic analog of relative topological Hochschild homology, and out of that, we've gotten new invariants of green functors. We have a theory of twisted Hochschild homology for green functors. We also get a theory of Witt vectors for green functors. But you might wonder, I think a good question is, does this tell you anything about the classical theory? So let me say 5 minutes about whether this tells you anything classical.
Was A now an FE algebra?
In my classical?
Yeah.
Yeah, I'm going to let A be a ring, and I'm going to let H be the trivial group, and I'm going to see what this tells me. So, for any ring. So I'm going to let A be a ring, and then H is the trivial group, and we could ask, does this tell us anything? So remember my picture from the very beginning was maybe I'm interested in algebraic K-theory, I have this trace map to topological Hochschild homology, and that has a linearization map to Hochschild homology. So A is a ring, so that's all classical. And then I had this picture which said, well, actually I'm interested in these TR groups. I need to be able to compute TR, say n plus 1, Q of A at P, and my trace maps, they lift. And well, I have this vertical map. This is some iterated Frobenius map. And so then a really natural question is there something that goes here? So is there an algebraic analog of TR that receives a trace map from K-theory lifting the ordinary Dennis trace? And the answer is yes, and we can see it from this perspective. So how do I do that? Well, what is this thing? This is fixed points of topological Hochschild homology. So this is pi q, say Cp to the n, of THH of A, Cp to the n mod Cp to the n. So that is like a really complicated way of writing a TR group as a Mackey functor evaluated on some orbit. But if you write it that way, then what we've done so far, these linearization maps, which maybe are not up here right now, tell us that we have a map from there to the twisted Hochschild homology for Cp to the n of the ring A evaluated on that orbit. So that tells you that you do have a map from, you do have a trace map from algebraic K-theory to this twisted Hochschild homology. Ideally, we would like that to be a lift of the Dennis trace. So how do we see that that's a lift of the Dennis trace? Well, that actually just kind of falls out because here I claim that I have a Mackey functor restriction map. And in order to see that, you need to know that the classical Hochschild homology agrees with the twisted Hochschild homology of the ring if we evaluate on the orbit Cp to the n mod the trivial group. Okay, so I do get a trace map to my twisted Hochschild homology lifting the classical Dennis trace. And the very last thing that you would want, which I don't have time to say in any detail, so maybe I'll just say in words, but the very last thing that you would want is to deal with that restriction map. So in the THH story, it was so important to know about the restriction coming from the cyclotomic structure. So we would also want an analog of that restriction map R, which was a map from TRN to TRN minus 1. And this is the map that I said specifically doesn't just fall out of the Mackey functor structure on TR. So, and you wouldn't expect it to. This was sort of dependent on the fact that THH is cyclotomic. So this is where we used that cyclotomic structure. And so what do we do to come up with an analog of R? Well, another piece of this work, which I won't go into, is that we define what it means to take geometric fixed points of a Mackey functor, which you can roughly think of as killing off things coming from orbits G mod H, where H does not include n. I always mess that up. So we can define geometric fixed points of a Mackey functor, and we can use that to prove a type of cyclotomic structure. So a type of cyclotomic structure. And that was all very vague, but what that means in the case where A is a ring is that it gives us maps which are analogous to these R maps. It gives us maps from the Cp to the n twisted Hochschild homology of a ring on the orbit Cp to the n mod Cp to the n to the Cp to the n minus 1 twisted Hochschild homology of A, the orbit Cp to the n minus 1 mod Cp to the n minus 1. And we're supposed to think of these as being an approximation to the restriction map. And so you could ask, well, what does that give me? So the last thing I'll say is that In classical trace methods, one thing that you look at is we use the notation TR for, well, let's do this, for the limit over the R maps of the TRNs. And that thing is computationally useful. So we could define an algebraic analog like that here. We could define an algebraic TR, which will be the limit over these quote R maps, which I hesitate to call the restriction because they're not the restriction maps in the Mackey functor, but I don't know, whatever you want to call that map. We take the limit over that map of these twisted Hochschild homology things. And you could call that some algebraic approximation to TR. And so we did one computation, which was FP. And so what do you get here if you do this for FP? Well, algebraic TR of FP at P turns out to be, and this follows not so hard from the computation we did earlier if you compute these maps. This turns out to be the p-adics when k is 0 and 0 otherwise. So I'm supposed to think of this as an algebraic approximation to TR, or maybe to algebraic K-theory, and what this says is, well, in this one example, this is a great approximation, right, because this is the answer for these TR groups as well. Okay, so this is what you get for topological TR, is you get p-adics in degree 0 and 0 above. It's also what you get for the p-completion of K-theory at FP. So not claiming that this is what happens in general, but in this one example, the algebraic approximation completely captures what happens in the topology. Okay, I'm out of time, so I'll stop.
Can you say what happens for, say, polynomial rings over FP?
Not here. So we have some like, well, the only example we've computed all the way to algebraic TR is FP. But we do know, like, we have some splitting results, like you would expect the usual thing that if you take the topological Hochschild homology of a pointed monoid algebra, you get a splitting as the THH of A smashes cyclic bar construction. So we see that kind of splitting result on the chain level in our twisted Hochschild homology, but which you could use for a polynomial algebra type thing, but we haven't carried that all the way through to here. So,
like related to the Durham-Witt complex.
Yeah, it should be. I have nothing concrete to say about that, though.
So the geometric fixed points of a Mackey functor, what kind of object is that?
The geometric fixed point, so, right, I was really sloppy. Okay, so let's say M is a G Mackey functor and N is normal in G, then the N geometric fixed points of M is going to spit out a G mod N Mackey functor.
Is that does that depend on G being cyclic, or is that for any G?
No, that part is more general. And it's like, it's kind of what you would think, like we define like a Mackey functor EF for the Burnside Mackey functor, and then EF tilde is like the Burnside Mackey functor modulo that sub Mackey functor, and so it like kills all the appropriate orbits and stuff. So the sort of thing that you would think to do basically goes through.
But left to draw into some restriction in the other direction? Inflation or?
The geometric fixed points? Tyler says yes, so I'm going to go with that yes.
I think it's something which is not ordered in N, not restriction or
if you wanted to calculate not classical algebraic K-theory, because that wasn't hard enough, and you wanted to calculate equivariant algebraic K-theory, like in Mona sense or something, does this help?
Yeah, it's an excellent question. Yeah, so a very natural question is like, what kind of trace maps does the actual H relative, THH or TC or TR, what does that receive? And I don't have an answer for that, but it should be from some kind of equivariant notion of K-theory, not from ordinary algebraic K-theory, and so there may be something there, but I haven't thought about it. Yeah.
Why don't you define the geometric fixed points just as pi naught of the sort of spectrum level geometric fixed point?
It agrees. So, I mean, what we have is like a more constructive definition that sort of allows you to study it a little bit better, but we show that it agrees with doing that, which is what you would expect, right? A lot of these Mackey functor constructions are like pi naught of spectrum level constructions, and so yeah, it is.
I have a question. non-equivariantly, you can view Hochschild homology as THH relative to the kind of McLean spectrum of the ground ring, at least if you think of Hochschild homology in the derived sense. Would this be a way to understand your equivariant version of Hochschild homology?
Well, so this is like the non-derived version of that. So like what you're saying is that the relative over HZ, say, gives you like the Shukla homology. And so we do construct a Shukla homology version of this. So we, this is not that. So what I told you about is like the non-derived version. You can do a derived version. Turns out that's actually a little bit more complicated because of like weird homological stuff about Mackey functors, where I defined my green functors to be commutative, but you really need to work more in an associative world if you're going to do this Shukla homology version. But yeah, I mean, we do that construction, but we don't really use it for anything yet.
That would be a lot easier if being flat is actually a thing that happens.
There we go. That would make life easier.
Okay, then let's think. Yeah.